don't have $1,000 to spend on a demo robot, you know, one with all kinds of sensors, servos, gyro, accelerometer, maybe a laser LIDAR, buttons and lights and stuff like that? No worries. My name's Sid Faber. I'm from the robotics team at Canonical, and I'm going to get you up and running with a Turtlebot3 robot running in a simulator, everything open source. In this video, we're going to fire up a Turtlebot3 simulator. It's a really cool robot. It's got a bunch of advanced sensors and related software, and it's specifically built for training. The Waffle Pi retails for about $1,400, but all the software used for it and used to simulate it is all available open source. So before we install the simulator, let's take a look at my Turtlebot just to see what it does. So here's a look at my Turtlebot3 Waffle Pi. You'll notice it looks a little bit different from the standard build. That's so that I could get access to the boards and add and remove SD cards and other connectors on there. Also with it, you'll see it comes with a power supply, standard laptop power supply that we can connect to the OpenCR board, as well as a joystick controller. This has a Bluetooth transmitter on it that connects to the Bluetooth receiver that's on the robot. So let's look at the robot itself. As I mentioned, there's Bluetooth. This is where the Bluetooth receiver sits on my robot. Again, connects to the joystick. The next thing you'll notice right off is the LIDAR, or the laser distance sensor. When the robot's running, this will spin around and just simply take a distance measurement at different angles. That has a small board that connects via USB to the Raspberry Pi. Also, the Raspberry Pi has a standard Raspberry Pi camera connected to it, and we'll be able to access that through ROS. Next thing you'll notice are the boards. So obviously this is the Raspberry Pi, just a standard Pi 3B Plus, and then the OpenCR board. The OpenCR board has a power supply over here where we can connect in power here, and it will provide power to the rest of the robot, as well as there's the master on-off switch here. There's a battery that can be used to drive the robot as well. It's a 12-volt battery that connects to the OpenCR board. You notice on the CR board, this is our motor controller board, a number of different connectors, Arduino style, Raspberry Pi style, UART, TTL, and so on. There's also two connectors here to the wheels. The wheels are actually Dynamixel servos. So they're not standard DC motors, they're actually servos where you can control exactly what angle they move to. It gives us a lot of control over the robot movement. Also, there are other sensors built into the OpenCR board that we'll be able to access, gyroscope, accelerometer, and so on. Also on the board, there's a few general purpose push buttons, so just simple switches that we can access through software. Also, a few general purpose LEDs that we can turn on and off through software. So those are the things that we should expect to be able to access in our simulator in our model Turtlebot3. Pretty cool, right? That's why this is so great for training. But in order to run this in a simulator, all of those things have to be programmed in. So what is a simulator? What's the big deal? Well, when working with robots, it's not enough to just throw some random sensor readings into the software. You actually need to simulate the real world. You need physics. With Gazebo, you can actually simulate a laser rangefinder that's going to return real values based on where the robot sits and moves within its environment. When you set up your models properly, the simulator will figure out things like collision with other objects, even forces and torque and speed and so on. Plus, it actually gives you a realistic 3D rendering of the robot's environment. It's just like a video game. There's a lot of work in building out the simulation, but thankfully Open Robotics has produced a robot model for us that's pretty robust, and we can use it to explore a couple of worlds that are also provided with it. And this is all open source again, so all we have to do is the installation. Let's get started. First thing we need to do is to create an Ubuntu LXD container set up for ROS and then install ros-foxy-desktop. Oh, here you can see the container wasn't done initializing. Let's give this a second. The LXD setup was covered in an earlier video, but any ros-foxy installation will do. And since we're targeting ros-foxy, we need to be running Ubuntu 20.04 in our container. This also gets us associated with version 11 of the Gazebo simulator. Like with any ROS install, we want to add the setup file to the bashrc and source it. Now let's take a look at the Turtlebot instructions to see how to proceed. You can find them by working your way through the robotics.com website, or you can simply Google for Robotics Turtlebot. We want to use this Turtlebot3 e-manual. There's lots of good information in this manual about the Turtlebot. We're going to focus on simulating this in ROS2. We're simulating in Gazebo, not Fake Node. We're also going to run within ROS using the Turtlebot3 Gazebo package. As you can see, this means that first we have to install the Turtlebot. The e-manual gives the instructions for the ROS2 installation that we'll need to follow. We're following the PC setup. So here you can see we need to install Gazebo, we need to install colcon, which is the ROS build system, and we need to install Vcs Tool. Okay, so here we'll install the Python 3 colcon common extensions. Again, colcon is how ROS packages are built. It's a wrapper for traditional make commands for a complex environment like ROS. Next, we'll install Gazebo. We're installing Gazebo 11, which works quite well with ros-foxy. Even though the Robotics docs are still documented for ROS dashing and Gazebo 9, we can install it on ros-foxy with Gazebo 11. Everything works fine. Then we're going to install VCS Tool. This is a real simple utility. It just lets us download a bunch of repositories all at once. Now we'll make the directory where we install the Turtlebot source, change into that directory. And then I need to grab a wget instruction from the Robotics manual. This file we're downloading has all the repositories that we're going to use to import with the VCS tool. Okay, use VCS import to import the repositories. Make sure you get the syntax right. Now all the source code is downloaded into our source directory, so it's time to build. We're going to use the standard colcon build command and let it rip. So the Turtlebot is now built and installed. All we need to do is a little bit of environment configuration. Like always, we'll add the Turtlebot setup.bash file to the bashrc, so that way we path in all the Turtlebot components. Then let's go back to the Robotics instructions for ROS2 simulation. There's a Gazebo model path variable that needs to be set, so we'll just do a copy paste for that. There's one more environment variable here below, the TB3 model variable. This specifies which Turtlebot you're going to be running or simulating. We're going to be doing a waffle pie, but if you want to simulate a burger, just change this variable and you're good to go. We'll put that in our bashrc, and now that everything's set up, we'll source the bashrc, and we're done. Okay, we'll launch the simulator using the launch command from the e-manual. First time through, this may take a bit, so you just have to be a little bit patient. Here we are. This is a Turtlebot3 running in an empty world in Gazebo. The blue circle with the lines are the LIDAR range measurements. The rectangle is the camera view off the Pi camera on the robot. Let's launch this again, but use a more interesting world. Let's try the house. We'll put that in the background and run a few ROS commands. As you can see, there's a full ROS graph of topics, nodes, and services all within our simulated robot. There's a lot to mess around here, but let's just close this down for now and start up with an empty world again, because I want to drive the Turtlebot around. So we'll launch Gazebo again with an empty world, and then let's put that in the background. And then run a teleop keyboard node so I can control it from the keyboard. Zoom in a bit. Here you can see we're moving around. I'm going to leave it to you to drive around a house or some other simulated world. Hopefully you found that as cool as I did. We're going to be using this simulator a lot to look at more of the ROS internals until we start building our own robots. Thanks a lot for watching. Again, my name is Sid Faber from the robotics team at Canonical. See you next time.